Okay, so far most of our discussions onwards, the discussion was on hardware, right? CPU, memory, clusters, switch, but now we are going to think of programming. Okay, so programming also there are various kinds of programming scheme. So I am sure all of you know how to write sequential program. Sequential program is basically you run on a single CPU. Okay. So, now we will start thinking about how to use more CPUs and more GPUs, well single GPU and more GPUs. Okay. So, let us see in what ways you can program. In fact, there are many ways to do parallel programming, and you choose one which is most suitable for you. Okay. So, that is what is today's discussion. So, the most dominant paradigm or most dominant scheme is single program multiple data. Okay. It's in fact surprising when you start doing parallel programming, you will be surprised that if you have let us say 4 machines, 4 CPUs, the same program runs on the 4 CPUs, same program, but they work on different data sets. Okay. So, you have to write in such a way that you have to tell the program within a program. So, same program is running. So, the guy, how will the first guy know what I have to do? So, you basically have to say that okay, if you are the first guy, take the first chunk of data. If you are the second person, second CPU, then you take the second chunk, third CPU, third chunk, and fourth CPU, fourth chunk. So, this has to be part of the program, but depending on the CPU index. So, we will index the CPU, it will do all that operation, and all of them do the same operation, but the data is different. I hope it is clear. Okay. So, the same program runs on all of them, and data is different. Okay. Now, once we start writing the program, then we will understand. Okay. But please keep in mind that is single program multiple data, is not that different programs are running on different CPUs. Okay. That is the most dominant paradigm. There are ways to do different programs also, but in fact, in our course we will focus on this single program multiple data. So, this is called SPMD. Okay. It is not SIMD, single instruction multiple data is for CPU hardware, okay, but we are doing now single program multiple data. So, single program runs on all processes. In fact, when I started doing parallel programming, this is what you have to think, same program is running, how do I tell this guy to do that, this guy to do that, how to talk. Okay. So, we need to just kind of get used to it and think on that line. So, I am going to use all 4 CPUs.
But it will copy the same program in the
No, well, yeah, same program is running. So, well, it is not very difficult to think about how this program. So, this is my data, okay, data. So, divide in 4 parts. Okay. Now, I have 4 CPUs. P0, P1, P2, P3. Okay. I am going to P0. So, this is the data connections. So, P0 will do the first one, second one, and so on. So, now in the code you have, so same program will run. So, what I am going to do is, so every CPU has its ID, it is called process ID, PID. Processor ID is not the process ID of, let us call it my ID. Okay. So, the first guy has 0, 1, 2, 3, in fact, that is standard, it is assigned by the operating system itself. Okay. So, 0, 1, 2, 3. So, then you say, well, in the program you have to write, if my ID is I. Okay. So, depending on my ID I am going to pick that particular data. So, I should not say my ID. So, my data set, my data will be A I star. So, let us say this is so total data is n. So, this will be n by 4, right. So, I just say multiply I n by 4 colon in Python language colon I plus 1 n by 4 minus 1. Okay. So, these are data which I am going to work with. So, this will be written inside the program. Okay. I is my process. So, this is my index, process index, my ID. So, instead of I write my ID. So, the data I am going to use is my ID star n by 4 and my ID plus 1 n by 4 minus 1. So, you see if it I is 0, then it is going to be 0 to n by 4 minus 1, with 1 then n by 4 to n by 2 minus 1. So, it is going to take the data like that. So, it is not difficult, you just have to get used to it, and then the same program will run, but with this data. Okay. Then if I want to add the number, then I will say for loop I equal to 1 for data, okay, make sum the data, okay. And where should I put? You should put in my sum. So, this is going to be the sum of each processor. Okay. This number will be different for different processors. Okay. So, all of them, once this part is done, we have local sums. Then I am going to ask some person to do the total. So, normally the P0 does the local total. Okay. This is called master ID, master processor. Okay. So, master processor. So, if my ID equal to 0, or if I am the master ID, then get local sum. So, this is where communication will be involved. So, I am going to ask each processor to send the data, okay, and then add all the same, add local sum, and that is sent to variable called sum, and then print sum. So, you get the idea, no? So, the same program will run, this program will run on all processors, but depending on my ID, I will be able to do my task. Okay. So, this is how it is done. I mean, it is not difficult. Okay. So, may need to communicate among processors, as I said, sum will be local sum will be sent to the master, and result is collated by the master. So, I just said. Okay. So, that is how it is done. So, what I did right now gave a sketch of a MPI program, message passing interface, but if it is a shared memory, then actually it is very similar. Okay. Local sum and then sum it up. So, shared memory use OpenMP, I did say something on that in the last class, and P threads. Okay. P thread is more complicated, but we will just use OpenMP, and with distributed memory we use MPI. Okay. So, this course is basically going to focus on not focus on, it will be these two I will cover maybe around 4 classes. Okay. This is one of the traditional programming environment, programming style. Now, there are situations we have multiple program, multiple data. That means, that separate programs are running for separate data. So, one thing could be, well, I mean, one example is human body. No? So, heart is not running the same program as my kidney, they are running different programs, or they have different functions. So, this is different programs are running for different systems. So, well, this is not we do not have computer program for human body, but we have program for earth and atmospheric simulations. So, for atmosphere we have ocean, land, ice, CO2 chemicals, aerosols. So, it is possible that you can write separate programs and they communicate to each other when needed. Okay. So, in fact, it is doable. I mean, it is not everybody can write those programs. So, we have in a computer several programs are running. Okay. In our laptop we have browser, we have email, and all that is running, right, and we can communicate, right. I mean, you can basically from browser you take some data and copy it in a doc file. Okay. So, that is a kind of communication between, well, that is basically some interaction between two programs. So, same thing can be done among various programs, but is difficult. I mean, no, not everybody can do it. One thing is, suppose we are doing a CFD simulation, okay, of a car. So, the data output will be very big, right, a huge amount of data is being simulated. Now, I want to do a real time visualization. Okay. So, we want to do a 3D visualization of real time, then we do not want the same program which is solving the differential equation to do this visualization part. So, it is possible that you can write a program which is for visualization with this special software, and that software will pick the data and render it. So, that communication between two different programs, one for visualization and one for PDE solver, and they will talk only when data is, well, it should be very frequent. I mean, every second some data should be coming, so that we can update my frame. Okay. So, these are done, but they are not easy and we do not do it in this course. Okay. So, this is not a very popular style, but as I said, people do this stuff. It is not that they do not do it, but this is not part of a generic, I mean, yeah. So, specialists are required for doing this kind of programming. Okay. So, we need to now look at some concepts, how good is your parallel program, okay, and what is the best you can do. Okay. So, there are two things called, well, basically we need to do what is speed up, okay, and efficiency is connected to speed up. I will just write that in a minute. So, there are two ways to compute speed up. Okay. So, I will give you the first speed up. So, I have a data, okay. I may, let us imagine that I have a matrix and I am summing all the elements of a matrix or doing something on the matrix. Okay. So, this size is M, matrix size. So, serial, if I take a single core, well, by the way, I should not use single CPU, which is often used, but that is not correct. So, within a CPU there are many cores, right. So, it is good idea to say for a single core how much time will it take, and if you have more cores how much time will it take. Okay. So, like ROM processor has 64 cores. So, I would want ideally that if my sequential program takes, let us say 1 hour, then my parallel program should take 1 by 60 hour, which is like 1 minute. Okay. So, that is how we would wish, right. That so this is what this formula is telling. If the data is the same, please keep in mind the data must be of same size. So, speed up is serial divided by parallel. So, parallel is with 60 processors. If you use more processors than same data, it should speed up. So, for 60 processors, I should expect speed up to be 60. Well, that is not the ideal wish. Okay, you will not get 60, but okay, if you get 50, you should be happy. Okay. No, is correct. Serial is will take more time. Oh, okay. Speed up is greater than 1. So, ideally is P is the number of processors, okay, or N. I am going to use N as a symbol for processors. Okay. If N is the number of processors or number of cores, let me just put number of cores, and efficiency is S by. So, for 60 processors, ideal scaling is 60, ideal speed up is 60. So, efficiency will be 60 by 60 is 1, but I will not get 60, I probably get 50 with 60%. So, 50 by 60 will be the efficiency. Okay. If my program is too complicated, then I may not get even 50, I may get around 10. Okay. So, efficiency will be 1/6. Okay. So, what is ideal speed up and how much you get, that is efficiency. Okay. Now, so this T parallel is, so how do you come, I mean what do you expect for T parallel to be? So, you have P processors. Okay. So, it will be T serial divided by P. So, if it is all computation, okay, then it would be these two should match, but things are not all computation, right. Some communication is also required, some data to be sent, or some you need to create data in the beginning. So, you are setting up your system. I mean the in the beginning I am going to assign IDs for all the processors. So, before the exams or something starts, there is some setting up time. Okay. That is not part of the computation, but mostly I would say the overhead which is not discussed in old textbooks, but the overhead is communication, that is what you should think. So, this part is for computation, but overhead is basically communication, which is a problem. Okay. Or not a problem, well, communication is not a problem because we need to communicate, but it is overhead, that is why your efficiency will be less than 1. So, there are several laws or several scaling relations. Okay. So, this is called one of them, first is Amdahl's law. This is also called strong scaling. So, please pay attention to the derivation. So, this is what in fact it tells you something about limitation of parallel programs. So, simulation with m data points. So, my data points are fixed. So, imagine I have a 3D grid or matrix, so my m is fixed, but I am going to work with n processors. Okay. So, the total time, so imagine part of it, some is parallelizable or some is not parallelizable. For example, setting up the arrays, okay, in the beginning. So, the part which is not parallelizable, which is I am going to call it serial, T serial, and then this is called T parallel, which is everybody is doing it. Now, these are standard derivation which is there in Wikipedia, for example, or textbooks, but I would add another thing called T communication, okay, which is not included in the general derivation, but T communication is very important, which I am going to show you a bit later, that this is one of the major spoiler of efficiency. But let us imagine that T communication is 0. Okay. For this derivation we assume the T communication is 0. Okay. So, for if I have only single CPU or single processor, then single core, then it will be T serial plus T parallel. But if we use n processors, then serial cannot change, serial will remain, it will take same time, but parallel part will be decreased. Okay. Suppose something is taking 1 hour, the serial part which took something like 3 minutes. So, 3 minutes each processor has to spend the 3 minutes, but then other part which was for a single program, it was 57 minutes, that will be done jointly, and they will decrease the number of processors, assuming that it is equal division, it is all computation. So, this will be T p by n. Okay, is reasonable, no? With the assumption that the parallel part is equally divided and it is done efficiently. Okay. So, so let us use a variable called f, which is T parallel by T total time. Okay. So, that is like a fraction. So, you can compute that 57 minutes of which is to be parallel, which can be parallelized. So, 57 by 60 will be f. Okay. So, total time, by the way, this total time T is for single processor. Okay. That is so, this is formula. Now, I am going to write down, let us go to T prime. Okay. So, this T prime, which is this with n processors, I just rewrite like that, add and subtract T p. Okay. Now, what is T prime by T? So, I just divide the whole thing by total time, which is T s plus total time. Okay. So, this is total time, this part. So, that will give us 1. This T p by capital T is f by definition, and this T p by n is by T is f by n. So, T prime by T is this. Now, what is efficiency? It is single processor time divided by parallel processing time. So, it is inverse T by T prime, which is 1 divided by 1 minus f plus f by n. Okay. Now, if f equal to 1, then I get speed up to be, if f is 1, then speed up will be n, right, which is ideal. So, 1 minus 1 will cancel, and this will be 1 by n. So, that is ideal when f is 1, the whole code is parallelized, but there are situations where not every part is parallelized, and then we get efficiency less than speed up less than n. Okay. So, we can, so there is a bound here, this number is always greater than 1, greater than 0, sorry, greater than 0. So, speed up is always less than 1 divided by 1 minus f. So, imagine that I can parallelize 90% of the code. Okay. So, I parallelize 90% of the code, but so f will be 0.9. So, what will be s, max s? Well, this s will be 1 by 0.1, which is 10. So, my speed up is less than 10. So, you may use 1000 processor expecting 1000 times speed up, but your code is only 90% parallelized. So, you will never get more than 10. Okay. So, this is a major, I mean, this is a nice theorem which tells you that you should not just use more and more processors. You should make sure that almost all parts of your code is parallelized. Is that clear, this derivation? So, this is I just did it in Python. So, n is the number of processors or number of cores, I should say, and s is the speed up. So, I have 100 processors maximum, and the best speed up I can get is well, depends on f. F is 0.95, then I will, I am just, well, I mean, I get around 17 or 18. So, though I have 100 processors and 95% of the code is parallelized, but I get only around 17, 18. Okay. So, this number is quite small. Okay. So, that basically that 1 divided by 1 minus f is what is dominant, and for 0.95 it is 20, right. This part 1 divided by 1 minus f is 20 for 0.95. So, this is called strong scaling in technical language. So, if your data is fixed, if I put more resources, that means more scores, then I expect speed up as n. So, data size is fixed, but I am putting more resource. But the second scaling is called weak scaling, where I increase my resource, but also increase my data. Okay. So, suppose somebody gives me double the processors from 20 to 40, but increases the data size to double as well, okay, from 1 billion data points to 2 billion data points. So, what do you expect? Ideally, it should be same time, right. So, if you increase your complexity, data complexity as well as the number of processors. So, this is called weak scaling, and your code should have both weak scaling and strong scaling. Okay, that is a good code. So, some codes show strong scaling, but not weak scaling, and some show good weak scaling and not strong scaling, and it is connected with many factors, okay, like cache and data transmission and all that. So, it is quite easy. Suppose my use more and more processors, and I am using of course more means let us say 10,000 processors. Okay, right now people use 100,000 processor very routinely, but then if my data size is small, I am using only let us say million points, that is a very bad idea, because for communication how much data will be sending across one to next processor? Tiny, I mean maybe you are sending only 10 data points or 15 data points. So, it will have lot of overheads, latency, and there is waste of time. Okay. So, if data is big, then only you should use more processors. Unfortunately, these are not what people do in our computer center. Okay. We have course, run it, and so that is a very bad way to use our computer resource. So, simulation with m star n data points with n processors. So, you understand, no, I increase n, so my data size also increase. Okay. Now, let us see what is the speed up. We will define similar formula. Okay. So, time for sequential part is T s, at the time for well same thing as before. So, total time for a single processor will be T s plus T p, and number of operations, floating point operations will be T s plus T p times flops. Okay. So, if I n processors, then so my data size is also increased. Okay. So, basically this T p, so I increase the data size. So, the time taken will be well, time taken will be okay. So, what do I expect? If I increase my number of processor and data, so T p should remain the same, no? But T s will be, T s also will be the same, but so basically it should, so T p times n will be the times flop. Flop is the number of operations per second. So, this is the total number of operations per second for all the n processors. Okay. So, ratio. So, basically in, so I would say in the same time, my time is same T s plus T p. So, in the same time how many operations I could do with n processor and how much operation I did with one processor. Ideally expect that I should be doing n times more, but it is not n times more, it is ratio of the two. So, this T s is spoiling it. Okay. If T s was 0, then I would get n, but T s is not 0, then I am just going to divide this 2. So, this is I rewrote exactly like before. So, T s plus T p minus T p plus T p by n, flop will cancel, T s plus T p. So, that will give us 1 minus f plus n f. So, in some sense it is T prime by T in the earlier derivation is just the other ratio. Okay. So, it is 1 minus f plus n f, not divide by n, sorry I made a mistake, multiplied by n, that is another difference. So, number of operations in same time, how much with n processor and how much with n with one processor. Okay. So, this is basic, well I mean so this is our speed up. If f is 0, no, f is 1, sorry, if is 1, then it will be n. Okay. But if it is less than 1, then it will be less than n, and but it is interesting, it is linear in n. So, this is the plot. So, S is 1 minus f plus n f. So, with the 0.95, I am this black curve, I am reaching close to 100, is I do not know, this is probably 95 or something. Okay. So, weak scaling is linear in n, but these are classic derivations and with basically old derivations. With modern machines, these formulas are not very useful. Well, ideas are useful, but there are some more very critical complications which come. Okay. So, which I will describe after this example. So, this is the example from this website. This Julius set generator. Okay. So, this is a fractal in fact object. So, the grid point is this 10,000 by 2000. okay, and number of threads, or well, you can just think of number of cores. For one core, the time taken is 3.932 seconds. So, my grid size is not changing, if you see, it is same grid size, but I increase the number of threads. So, my time should decrease. Okay. So, this author has gone up to 24 processors, and but the best time is well 0.262, and you can plot it. So, speed up versus number of threads. It is not linear, okay, and in fact, it is saturating. So, with 24 I would have expected something like 24, but it is not 24, it is something like 15 or so. Okay. So, this strong scaling. Resources is we get more resource by same data. Resource means CPU. Okay. Now, we can do the weak scaling for this for 0.97. Well, I mean, if I do the fit, I get 0.97 as f. So, 97% of the code is parallel. By the 0.03% is basically initial setting up. The code is looks very will look parallel to you. If you show you the code, it will look parallel. But initial setting up is everybody has to do it. In this other experiment, you can see that number of threads is increasing, but also the number of data points are increasing. So, width is the same, but the height is increasing by twice every time. So, data points is increasing and the thread is also increasing. In fact, the proportional. So, time is roughly, when you see the time is roughly the same, but a slight increase in time. Okay. So, the speed up will be less than n because of that. So, this is speed up curve. This less, well, I do not know, it is around 22 or something. Okay. Time taken is increasing, yes. Okay. So, ideally it would be same time, but it is not ideal. So, time taken is increasing. Okay. Okay. So, f is if I do a fit, I get 0.9. In fact, not me, I mean the person has done the fit is 0.9. Okay. Now, I would say that you can fit in this earlier formula what I was doing T, TS, TP, and we should get 0.9. Okay. So, we need to do both weak scaling, strong scaling for your code. So, in fact, when you submit an application for a big machine, okay, and that big machine, they will ask you to do these two exercises and minimum 10,000 processors. Okay. Then only we will get a time for bigger runs. So, if your code does not scale for even 10,000 processors, then no way you can't get a computer time. Okay. So, that is a strict demand. So, to use those machines, you need to show your code is scaling well. Okay. So, problems with the above formulas. So, one thing is they assume 0 communication, right. So, I did not have factor T communication and no memory copy. Memory copy takes time. So, this is ignored altogether in this computation, and with more cores communication is very critical. So, they do not work for large n and large data. So, such programs, well, one moreover, T serial you can never measure. So, my data typically data is very big. Okay. So, single core it will take maybe 2 years. Okay. So, we can't compute T serial. So, the formula is T for parallel divided by T serial is basically waste. Okay. So, we have to compute time for different processors and make a fit, and the minimum number of processor will be 10,000, not less. Okay. So, but still we can instead of starting with 1, you can start with 100 or 10,000. So, you need to make a plot, x axis will be time processors, and we plot T inverse. Okay. If you plot time, then curve decreases like this. I do not plot speed up, okay. I just plot time, because we do not know what is f. Okay. So, speed up formula, that formula we do not use, we just compute t at t versus p will be like this, but we can put t inverse versus p, and this is straight line typically for good code. Okay. So, if it is straight and if its slope is 1, then it is perfect linear, but slope happens to be less than 1 typically. Okay. So, this is what we plot, and p starting point could be 10,000. So, from this we can compute whether it scales well or does not scale well, and that is how people do. Some people plot t versus p, which I do not like. Okay, that is I would prefer t versus p, or you can do log plot, then log plot will show straight line. Okay. These plots are typically log. Why? Because 10 power 4 to 10 power 6, 1 million processor. If you do linear, then then it's just going to, well, this is a log is a better idea, and okay, because t typically goes as p to the power alpha is a power law. So, log is a good, it looks good in the log curve, it's linear. In log scale it will be linear, right? Would you understand? So, log t is alpha log p plus constant. So, log t versus log p is linear. Okay, data spread over nodes, and communication is should be taken into account. Yeah, this is strong scaling. So, I am going to show you how to do weak scaling in this such plots. Okay. Okay. Strong scaling is this curve t is should go as p to the power alpha, ideally should be alpha equal to 1. Okay. Random data does not matter. So, basically is the data size. In fact, you should work with random data only, because if we imagine that all arrays are 1, then the compiler will be clever and will just give the answer, we will not sum it up. But if you random data, then it can't sum up by some algorithm or by guess, and it needs to compute all the numbers. So, look, if you have 1 billion numbers and one processor will take 1 hour, then 2 processors will take half an hour. So, this curve will show this kind of curve. Okay. Now, I am going to show you weak scaling how to do it. Okay. So, I am going to show you practical way to show weak scaling. Okay. Just give a minute. Okay. So, this is our own work. So, fast Fourier transform. Okay. Fast Fourier transform, which I will discuss it bit later, it involves lot of communications. So, this was work done on cluster called Shaheen, which is in Saudi Arabia, and the cluster was top, I am not sure, it was top 10 at one point, but it kept getting off from the slipping down. So, it has 196608 cores plus some more, but for computing this is what is available, like there is a management course. So, we use a full machine. Okay. So, this is full machine was used, and then we try to compute the scaling, okay, speed up. So, our code is called Tarang. So, it is a spectral code for solving fluids. Okay. So, minimum number of cores to be used is in this machine, there is a rule, it should be minimum is 2000 cores. Okay, you can't use less. So, T serial cannot be computed. So, we plot time taken for any number of processors versus, okay, T inverse versus processors. Okay. So, let us look at the plots, is quite easy. So, we make a model. So, as I said, there are lot of communication. So, we need to compute time for computation and communication separately. So, COMP is for computation, okay, short form, and COMM is communication. Okay. So, computation should scale linearly, right. So, expect that this gamma 1. So, if I have more processor, then time computation should drop linearly, right. So, gamma 1 should be is expected to be 1, okay. And communication is not expected to be 1. You have bigger data and more processors, then there are lot of traffic on the road, and in fact, this one everybody is talking to everybody. Okay. So, you see the 2 lakh processors are talking to 2 lakh processors. So, how much of communication taking place you can just imagine, like it is a huge number of communication. So, this gamma 2 is not 1. Okay. Now, there I mean you may make some estimates, you may get a theory, but it is just too complicated. We just do compute it by experiment. Now, total time it is T computation plus T communication, computation plus communication. So, T equal to T computation plus T communication. Okay. So, this is P minus gamma. So, if I do the inverse, I get P to the gamma. So, we compute 3 exponents from the plot, gamma 1, gamma 2 and gamma. So, let us look at this plot. It is the total time, and let me put both the plots here. So, this is T computation inverse versus processors. I am using P is for processors. Okay. So, so we compute T inverse computation versus P, and so it starts from 1000 processors, okay, and goes up to 2 lakh processors. 10 to the power 5 is 1 lakh, so 2 lakh processors, and we are doing for 768 cube, 1536 cube and 3072 cube. Okay. These are big data, okay, like 3072 cube is 10 billion points, okay, floating point, double precision. Now, you can easily see, well, I will just try to tell you a little bit more. Green curve is for 3072 cube. So, T is lying below 1536 cube. So, this is taking more time, no, it is the T inverse curve, not T. So, if you are below, then you are taking more time, and but they are all linear. In fact, I will show you the slope. Well, this slope is well, they are close to 1, okay, not so, not 1. Computation also is not 1, and that is because of cache issues. Like for example, here is getting worse. So, if it is going ahead, it is great, no, because I have more processors, time will decrease. So, T inverse will increase, but it is dropping down, that is bad news. And why it is coming down? For the reason why I just mentioned some time back. If you have less data, if you have more processor, less data, and less data is bad for transmission. So, there is so much time is spent on setting up your data, I mean okay, so latency is like a train should be reasonably full, otherwise it is not efficient. Okay. So, there are issues with the cache, the complex issues which come. So, it is very wishful thinking that I will get linear scaling, we do not get all the time. And T communication, in fact, you can read off from here for this, for let us say this curve. So, this is something like 20, okay. You can see this number. So, you know how to read the log curve, no, 10, 20, 30, 40, 60, it goes up to 100. So, you have to read like that, and because this log curve is not linear in when I go up. So, this is 20, close to 20, okay, maybe 18, and what is the corresponding number? So, the time will be 1 by 20, which is 0.05 seconds. This one is 200. So, T computation is 1 by 200, which is 0.005. So, computation is 10 times faster. So, which is taking more time, computation or communication? Communication taking 10 times more for 768 cube. Okay, and now imagine that what happens for bigger data. Well, it may scale, but yeah. So, these are the communication is the major bottleneck for this this package, and total is also scaling okay, but you can see this part is a problem. This part is problem for all of them. Now, we computed gamma 1, gamma 2, gamma 3. So, these are the numbers. So, gamma 1 is well 0.93 is close to 1, this is not doing well 0.79, is cache issues for sure, less data, not good. For cache we want to cache to be filled up fully. So, more data is good. So, parallel programming is typically if you have more data, then the code is, if it is written well, it will do well. Use less data, then it will not do so good. So, this is in fact is better than 1. Now, gamma 2 is around 0.5 and gamma is 0.43 to 0.64. So, it is that is what we get. Okay. And you can also see this scaling, the efficiency is we are getting something like 0.018. Okay. We did not compute efficiency by the formula I discussed, we just compute this one by how much is the, we can estimate how much number of operations, floating point operations is required for this operation, because each FFT we know the number is 5 n log n, when n is the number of data points. Okay. That many floating point operation will be done by this package for each FFT. So, and we know how much maximum operations, floating point operations can be done in this machine. So, we just divide flop of FFT divided by total max FFT, max flop, that is our efficiency. Okay. Okay. Now, this is very well, we say it is a good measure, but you can see the number, it is 0.018 or you can say 0.02. So, 2% only, right, that is efficiency. So, 98% of the time is lost, it is ready to do it, but it does not have the data. Okay. But it turns out even the finite difference, which is good for communication, people do not get more than 5%, 7%. Okay. So, big computers, this is a problem. Okay. So, weak scaling, now there were some questions how to do weak scaling. So, we have this plot T inverse versus P, right. So, these for 3 different data sets. Okay. So, 768 cube, 1536 cube and 3072 cube. So, I said well more processors, more data. So, you just divide P by data. Okay. So, we just normalized it n cube by 768 cube. Okay. So, multiplied by P, sorry, this is divided P divided by that. So, if I increase P by factor 2 or if increase n by factor 2, then P should be increased by factor 8, then I will get the same x axis point, correct. So, I want to for same value of x axis, what is T inverse. So, you can see that all these curves where they are scattered around, they collapse into a single curve. Okay. That means, for this curve the blue data point has 8 times more processors than pink curve, because of this n was doubled. So, P was 8 times. So, but they had same T inverse. If I increase P by 8 times and n by 2 times, then I get the same T inverse. So, these is weak scaling. Okay. So, this is what, so we can plot it and it is quite nice. This curve shows that our code shows good weak scaling. So, this code is good weak scale, shows both good scaling and strong scaling, except here. Okay. So, okay, that is how we had a pretty good number of core hours on this machine for later science applications. Now, we ran the same code on Selene, which is I think 9th ranked right now GPU cluster by NVIDIA. This is privately owned by NVIDIA. So, this is the paper which came up this year. He is our TA, okay, Manthan Verma is the TA. So, these are two guys are from NVIDIA. Okay. So, this is a collaboration of many people, and by the way, these 4 students, well, the 3 students, sorry, not 4 students, 3 students were in the course, the same course. So, this was work started from this same course. So, we are trying to port it to GPU. Okay. This is the first time the FFT was ported to GPU. So, these are the curves, same curve, computation and communication. So, we follow the same idea, and P is here now number of GPU, number of GPUs, not P is not the CPU core hours. So, you can go up to maximum 512 GPUs, okay, and computation you can see is perfect linear. Okay. So, so it is for double precision as well as single precision. So, this is for unfilled is single precision 32 bit, and this is for double precision. Okay. So, this our code can do both, and this is a CUDA. Okay. This is done by Manthan, he and other student also, so helped, but he is the lead person who wrote the whole thing in CUDA. This is before NVIDIA released its own CUDA code. So, this was first multi-node multi-GPU. So, it is running on 512 GPUs, and the 512 GPUs do not sit in single node, right. This machine has 8 GPUs per node, the DGX box. So, 512 by 8 is 64, right, 64 nodes, we ran on 64 nodes, and for different grids 1024, 2048 and 4096 cube. Now, this is, by the way, the slope, that slope, in fact, this slope is 1, I will show it is written here 0.9811. So, this one is a very good scaling for computation, gamma 1, but gamma 2 is not good. In fact, best is 0.69, which is here, and this because of communication. Okay. So, we will discuss FFT later, and it involves communication, and that is the biggest bottleneck, which is not curable bottleneck unless you have a very good switch. And I did tell you there is one Japanese supercomputer called Earth Simulator, which had this number. Well, now in fact, efficiency was 50%. So, we are getting 2%, and their efficiency was 50% for their FFT, and because they had a specialized switch. Okay. Now, weak scaling is again it is not falling in a straight line. Okay, we collapsed here. Okay, this is a collapse curve. For both are collapse curves, for this for single precision, double precision. This because GPUs, and I think we don't fully, I mean, this slope is not 1. So, this scattered quite a bit. Okay. So, weak scaling is not very good, it is not collapsing into single curve, not well understood, but that is what we get. Okay. So, with this I will end about what are the issues for parallel programming, and scaling is the critical thing. Okay. You need to perform scaling test for your code, and make sure your code scales well. That means, each part of the code should be parallel. To compute this for T computation, we put a, so there are functions for timer. So, you put a timer before the loop starts, and put a timer at the end of the loop of this FFT loop. So, computation is computation only, not setting up is not included in computation. In communication is, we also have this data sent from one processor to processor. So, there we put a timer start, timer end. So, we can put these timers and we can compute how much is when it is doing computation and when it is doing communication. So, these are separate computation and communication, or total is total of the whole code. It's those codes will be very complicated. So, how you can convert it is easy to guess. So, suppose we have a weather forecast model. So, we have one for the land, one for the sea. Then you can say if the process, well, you can divide the processors, 1 to 1000 will be for land, 1000, 1 to 1000, 2000 is for water or for the sea. Then if processor this, then I do this, if processor is this, then I do that. So, single code will basically merge two codes. You do not go inside and change the function, you just set of two codes, one below the other, you just put it like that, put if statement. But they will I mean scaling analysis of weather forecast codes is very difficult. Okay, they will just do the total time because they are, it is not like for loop, you know, it is a very complicated stuff. So, those scaling analysis is beyond, I mean you do not expect perfect scaling for sure, but you expect this kind of lines, linear lines, and there they will just put a single timer for beginning to end. You can't, well, I mean people, some small part you can do this computation communication separately, but it is too complicated. One more thing which is I did not include it here is called profiler. Okay, so let me just write this word profiler. So, profiler is which will basically take a code and tell you this 90% was time was done here, 5% was done here, 2% was done here, like that. So, then your job should be what? To optimize which part of the code? The one which spends 90% of the time. So, the profiler is very useful to see which part is taking most time, and people just spend try to optimize that part which is taking more time.